All right. I think we're getting close to 9 a.m. So good morning, Manila. Good morning, ADB. And welcome to ASEF 2024. I'm going to briefly introduce myself. I'm Matthew Mendes. I'm the Managing Director for Thematic International. Thematic is an implementing partner for many of the development institutions. We're based in Washington, D.C. We have about 6,000 staff located in around 60 countries around the world. And what we do is try to work for the implementing partners to implement their programs. Primary partner is USAID. Our motto is development works here. We work behind the scenes in the logos of our clients to deliver impact. I'm here today to lead and moderate the session on variable renewable energy and battery storage. I like to call it energy storage. I think we need to think of it a bit more broadly. I'd like to take a few minutes to set the scene. We're starting to see the implementation of solar, wind, run-of-river hydro, and other variable renewable energy sources. We've heard a lot about presentations about all of the emerging ones in ocean technology and tidal waves. Are all variable in many cases. And that presents a major issue for utilities who have had to, previously have not had to deal with this type of electricity. Most countries and the utilities are playing catch up now on how to manage the impact of VRE on their electricity grids. The issue of the sun shines during the day, but not at night when the loads are high. How do you manage that? If you have a heavy solar load, the wind is blowing when it feels like blowing, and you might have surplus electricity. What do you do with that? Some utilities have chosen to curtail RE as a management strategy. I think this is a bad idea. There are better solutions. Others have realized that one option is requiring dispatchable energy storage systems as part of VRE management strategy. This is obviously a better idea, but the question is economics, and we'll talk about that, and the availability of energy storage systems. In this session, I hope our presenters will try to answer some critical questions on how some of our countries are managing the growing supply of VRE in their power sectors. In the process, I'm asking them to answer some basic questions in their presentation as they're making those presentations, and we'll have a Q&A session. So I'm not going to take a lot of time to introduce their bios. You can get to them on the app. I want to give them the maximum time to talk, and I want to give the panel the maximum time and the audience the maximum time to ask questions. So we'll limit the presentations to 8 to 10 minutes. We will, after that, hopefully have 30 minutes for Q&A at the end and for audience participation. So some of the key questions. What are some of the reasonable strategies for accommodating growing VRE loads in the power sector? Think about those in terms of where you want VRE, when you want VRE, and how to manage it. What policy and regulatory changes are needed to accommodate the growing VRE load in power systems? What is the role of energy storage for balancing VRE loads? And remember that hydro is also a perfect storage system, and pumped hydro is probably the cheapest energy storage system that we have available. So think about cost effectiveness when you think about energy storage. What regulations, incentives, penalties are needed to trigger investments in balancing energy storage systems? And what are the different types of energy storage systems that are being deployed? So one of the things I want you to think about is that the utility of the future. I know that in the plenary session, someone outlined the view, but we're starting to live that. Not only are we having energy storage systems that we can have in the utility that companies put in place, but homes have batteries, cars have batteries. All of those things are now going to start playing a role. I live in a state of Maryland in the United States. We're the first state in the US to pass a law that mandates the utility to do V2G. That's vehicle to grid connections. That means my Tesla that sits in my garage 90% of the time unused can now be a storage device for the utility to dump power in and take power out. And I actually get a credit for it. So think outside the box when you're making your presentations in terms of options that we have, and hopefully we'll have a really good and healthy discussion. So with that, I would like to now invite Chris Blanksby, Principal Engineer for Antura, to present his paper on 10 years and 50 islands. Sorry, made a mistake. First, I want to invite Mr. Nambat Mend, project coordinator from the Mongolia Ministry of Energy, to present the Mongolian case study of variable renewable energy and battery energy storage, lessons learned. And this is, I believe, an ADB project. My apologies for the mistake on the listing there. So, Nambat, please.
Okay. Good morning, everyone. I'm a little nervous. So, my presentation has two parts, and first part is renewable energy in our country. Sorry, my coffee dosage exceeded. So, since 2007, Mongolia has been promoting promoting renewable energy laws and policies to support and promote renewable energy have been issued, and we are working to implement those policies. So you see the policies issued, and I would like to emphasize two milestones here. That in 2020, the government has set a plan to increase the share of renewable energy to 30% by 2030. In 2021, Mongolia joined the Paris and Glasgow agreements and promised to decrease energy sector greenhouse by 22.7%. So here you can see the share of energy sources. So in terms of structure and percentage of domestic energy sources, coal-fired power plants are still dominating. But it's good to note that the share of solar and wind sources in the country are increasing year by year. So among the renewable energy sources, solar and wind sources occupy the most part of renewable energy, and relatively stable hydropower plants need to be developed. As everyone knows, solar plants supply energy during the day, and wind farms have some fluctuations depending on their location, as there is wind or no wind. This is why we need more and more sources of regulating reserves. These include battery storage, hydropower plants, and pumped storage, and so on. So here we can see an example of daily load profile of our grid system. So for our grid, the peak load time is in the evening, and off-peak hours are at night. So that requiring ramp down and power from coal-fired power plants, and some curtailments for the wind plants. As you see, at the night time, the load of the grid is decreased. So Another factor that affects the operation of wind farms in our country is extremely cold temperature. And the fact that this cold temperature happens during the peak load winter season is also a challenge for us. And global warming has had a strong impact on Mongolia in recent years, causes a lot of rain in summer and extreme cold temperature in wintertime. So now I would like to talk how BESS is contributing to our grid system and renewable energy. So last year we completed the first utility scale energy storage project with the support of ADB, and it has capacity of 80 megawatt and 200 megawatt hours and has been operating reliably since it was put into operation in last December. It's shown daily grid load profile in the previous slide. The battery is charged during off-peak hours and supplying power to the grid during the evening peak load hours. This increases the potential for wind farms and supply more energy to the grid during the nighttime. So I like to show this photo that when we put into operation the BESS in December, last December, it was in the nighttime, the temperature drops below 30, minus 30 degrees. And the BESS was operating well in such harsh weather. So we are pleased to mention that within the scope of this project with ADB support and ADB's high-level technology fund, development of an ancillary service pricing policy and guidelines to attract private sector investment in scaling up BESS capacity in the future has been completed. So, and now there are several BESS projects with private and government investments in the development stage, which I think will be able to support more renewable energy penetration when they are put into operation. Yeah. So this is the end of my presentation. It's very short and brief. And if you see the charged and recharged amount of energy, now, for example, in April, the BESS operated with full capacity. Since put into operation last December 2023, our BESS is contributing wind energy as good as possible. Yeah. So this is the end of my presentation. Thank you.
That was actually an excellent introduction to this session, because you demonstrated in a country, Mongolia, which is, isolated for many of us, that you have the opportunity to actually do this. And the good news is I've seen solar with battery storage projects come in at lower than coal currently in competitive tenders. In the US, in Colorado, for example, we've seen hundreds of megawatts of solar with storage coming in at lower than coal, and wind with storage. So for a country even like Mongolia, where almost 80% of your power is being generated by coal, I think with the amount of land you have, it wouldn't take more than 1% of the land in Mongolia to generate all the solar electricity that you need. The key is going to be storage. Secondly, I know you need a lot of heat because it gets really cold in the wintertime. Ground source heat pumps today are very efficient, and they run on electricity. So we need electricity at night to run those ground source heating pumps. And so the battery storage project that you've done is amazing. All right, I'll stop talking. I have a habit of talking too much, but I'll introduce our next participant and presenter, Mr. Chris Blanksby. He's the principal engineer from Ventura, and he's going to present his paper on 10 years and 50 islands, the Pacific Islands Renewable Energy Journey. This should be interesting. Thank you.
Thanks very much, Matthew. So over the last 10 years, and probably actually a bit longer than that, Ventura has been helping to integrate variable renewable energy and battery storage into island mini-grids. There's I guess, a lot of differences between the different projects that we've done. Each one has its own characteristics. And just as an example, a project being developed in Solomon Islands has very different challenges to a project that we did in Ross Island in Antarctica. But what I want to focus on today is some of the similarities of those projects. And in particular, just to note that most of these projects are looking at between 60 to 90% renewable energy, so very high penetration systems, and some up to 100% renewable energy. The other thing that I'd probably like to just highlight as a commonality is that most of these systems are really technology leaders. These nations are taking on difficult challenges well in advance of where many of the developed nations, large grids are doing. And some of those lessons are really valuable to apply more broadly. So I'd just like to commend those countries. I took this photo about 10 years ago, and it's an example of a very well operated power station, a diesel power station. It has experienced operators drawing on more than 60 years of utility experience. It has everything that you really need to run a power system in one nice central package. You've got dispatchable power that can exactly match whatever the load in the grid is. It has all the other functions that a utility system has to provide. Frequency and voltage control, reactive power, spinning reserve, inertia, fault current, all the systems that make a power system reliable. Unfortunately, of course, there's the diesel fuel, which is expensive and generates greenhouse gas emissions, which of course brings us to renewable energy. So these photos are taken of various projects over the subsequent 10 years. And you notice there's a lot of solar, a lot of battery in there, there's a little bit of wind. And for my presentation, I really want to focus on that solar battery mix. Wind and hydro, I come from a hydro company, so I think it's a good thing, but they're very site specific and the development timeframes are quite long. And for that reason, we've seen a much faster acceleration in solar battery projects. And so I'm going to focus on them for the rest of the presentation and the lessons we learned from them. So the first thing, we've really got three key points. The first one is about battery energy storage. In 2014, we built a 3 megawatt mini grid, so quite a lot smaller than the Mongolia scenario, but back in 2014, this was a very sophisticated system. It included a supercapacitor battery, flywheel, dynamic resistors, and an advanced control system in order to coordinate so that it could run for several days at a time on wind and solar alone with no diesel generation. Nowadays, we can do pretty much the same thing using a grid-forming battery energy storage system all in one package. It does most of what the diesel generation can do. In the last 10 years, battery energy storage lifetime has pushed out from an optimistic 10 years out to 15, 20 years. They are much more standardised, there's better standards governing them, there's better fire safety and much better control systems to allow them to provide all the utility services. And of course, the price has come down quite a lot. But it's still very hard and very expensive and an economic challenge to do long duration battery energy storage. And that's the reason that most of the projects that we've worked on are sort of economically constrained to around that 60 to 90% renewable energy. We have done some projects that are 100% renewable energy, typically for small systems where it's easier to go out and deliver the whole lot at once. And this is an example of a project for a very small mini-grid, about 150 people, and it's purely solar battery system. There's no backup involved. On the left-hand side is a graph that shows the decision, I suppose, between the sizing of the battery. And in doing a solar battery system, the inevitable question is, well, what do you do when you have a week of cloud? How do you keep the power system running under that situation? And it gives me the opportunity to talk about the second key point, which is the value of demand-side management in being able to run a variable renewable energy system. Here we inevitably ended up sizing the battery for 5 days autonomy so that it could provide all the load to that system over the course of an extended cloudy period. But it's important to make a conscious decision about that, because if you look at it differently and size the battery smaller, such that on the left-hand side here, with a 1-day autonomy battery, we may have up to 2 weeks during the year where there is some load constraint. Critical loads can still be met, but there's some discretionary load reduction during that period. The trade-off is that the 1-day autonomy battery system costs about half of what the 5-day autonomy battery system costs. And so if you went to this end, you can effectively build 2 of these island mini-grids instead of 1. I'm not necessarily saying that one way is better than the other, just that it's an important consideration. The third point that I want to highlight is about the challenges of delivering projects for their whole life cycle. We've heard a lot this week about the opportunity, I guess, to leverage the private sector to accelerate renewable energy journey. And one of the things that I see as being particularly useful about that is the way that the return on investment for private sector can be tied into long-term performance of the plant through a PPA-style tariff arrangement, which really incentivises putting the right resources into operations and maintenance and asset renewal for those projects. But those same opportunities for the private sector are difficult, or a real challenge for very small mini-grids to access. And so what's difficult for local operators is to keep a power system running at optimum when there's infrequent faults that may not be obvious and require specialist skills to correct. So really what I want to advocate for here is a more programmed approach to, rather than just an initial CapEx investment in some of these projects, to delivering a life cycle solution that considers actively in the early planning stages budgeting for renewal of things like batteries over the project life and for regional training of operators. I think there's a lot of good initiatives along this front that are happening, and so I'd just like to encourage them to continue things that I've seen this week. So that pretty much brings me to the end. Just to recap the 3, I guess, main points. Solar battery systems are really expected to dominate in island locations. I think that batteries will really come into their own over the next 10 years. We'll see enormous developments there, and they'll become a critical utility asset in many ways. In doing that, I think there's still some really important decisions that need to be made about the, I guess, economic compromise between the size of the battery, the amount of renewable energy in the system, and the extent to which you can make perhaps difficult decisions around demand-side management to achieve high penetration renewable energy. And the last point, that there's a great opportunity to look more closely at life cycle delivery of mini-grids in small locations small mini grids to make sure that we get full value out of those systems. Thanks very much.
Thank you, Chris, for that very illuminating presentation. I really like the idea that you talked about demand-side management as being part of the solution. And what I would say is, as we move to VRE, it becomes a situation where you can generate power on rooftops, you can do it everywhere, you can have batteries everywhere. The solution is not just the utility trying to figure out how to do it, we all have to be part of the solution. And so managing our loads when there are cloudy days, maybe the air conditioner doesn't need to be that much higher, right? So those are the kinds of things that I think as we move forward, I see the dawn of the renewable energy age as one in which we democratize the way we use energy. Everybody has to be a player in this. Everybody has a chance to be a player. You might have an electric car with a battery. That could be a storage. We see virtual power plants coming up in California now, where everybody is part of that power plant. All right, next, I'd like to introduce Mai Tiwan, who is the manager for utility modernization at USAID's Southeast Asia Smart Power Program. She's going to present her paper on unlocking VRE grid integration in the Lao PDR. Thank you.
Thank you very much, Matthew, for the introduction. My presentation today would be sharing experience on unlocking variable energy, renewable energy in Lao PDR. We are working with the Laos government in supporting them in this area. So let me start with introducing the program that I am with. I am with this program called USA Southeast Asia Smart Power Program, or SPP. Our program is a 5-year program funded by US government, and we are aiming at deploying the advanced energy system and mobilizing the financing for those systems, as well as contributing to a 5% increase of power trade. We are working with a variety of partners such as ADB and ASEAN Center for Energy. We also work with private sector, the government, and the utilities in the Southeast Asian. For our work with Southeast Asian utility, we work with them to improve their performance by capacity building and technical assistance. One of the countries that we have been working with is Lao PDR. And this country begins to experience the VRE penetration. As of now, there are 12 solar PV projects with the site range between 2 to 15 megawatts connected to low and medium grid. The total installed capacity is 73 megawatts. And these are very little comparing to the what the country is committed to achieve in their NDC targets of 1,000 megawatts of wind and solar project in 2030. And the table here presents the list of the large-scale wind and solar projects that would help the country to achieve this NDC target. But I would also like to mention that there are a lot more of the small and medium size of wind and solar projects that are coming in this very near future. With the expectation of high VRE penetration, the country has to ensure that its regulatory framework is ready in place. Our SPP team works together with the Laos government, consisting of the Ministry of Energy and Mines and the state-owned utility called EDL, to do the gap assessment of the regulatory framework. We review each regulation, guideline, and standard as listed in this table. And in our analysis, we use the color code to represent how well each regulation covers the implication of wind and solar farm, as well as the rooftop solar. I will not spend a lot of time explaining this table, but in summary, in our analysis, we found that the existing regulatory framework is hydropower based, which is not surprising at all because the generation mix of the country is over 90% from hydropower. The framework partially cover the implication of wind and solar farm, but mostly do not cover the implication of the rooftop solar. And these are the gaps that our team are helping the country to address the gap. I would like to highlight our findings from the gap analysis for the Lao Grid Code here. The Lao Grid Code was developed over 10 years ago. It consists of rules for governing the connection, planning, operation, control, and maintenance of the transmission system. And in the table is the list of the chapter of the Lao Grid Code. Chapter 3, the connection procedures and requirements, is where most relevant to the VRE grid connection. And our analysis shows that the frequency, voltage, and non-technical requirements in this chapter needs to be modified to cover VRE grid connection at the high voltage level. How about the distribution level? The country currently has no official grid code or technical connection requirements for the distribution system, meaning that for the small or medium scale solar and wind farm, as well as the rooftop solar, there's currently no regulation for that. And this could impact the connection of these VRE projects to EDL grid in terms of the stability, safety, and power quality. So to close this gap, our SPP team, partnering with the Hawaii Natural Energy Institute, or HNEI, has been supporting the Laos government on this work stream called interconnection requirements for inverter-based resources. The timeline of support is 2 years, and we almost complete this support. For this support, we have 2 major tasks. The first task is to develop the interconnection requirements for IBR. We delivered 2 documents. The first one is the technical connection requirements for the transmission system, which we update the chapter 3 of Lao Grid Code, which already mentioned previously. And then the second document that we deliver to the government is the technical connection requirements for connecting VRE at the distribution system. The way we develop these 2 documents is that we refer to the international standards, mostly IEEE, and we work with the government closely to ensure that these connection requirements are suited for their context. We also deliver a capacity building workshop, actually just last month, for the government official to ensure that they understand the documents and they can apply this in their work. We invited speakers from utility to share their direct experience on connecting VRE to that grid as well in this workshop. And here come my the summaries of my presentation. I would like to share the lesson learned, and hopefully this can be helpful and useful for other international development practitioners as you are supporting other countries that probably has the similar context as Laos in the early stage of VRE penetration. So at first we ask this question: is the regulatory framework or is the grid ready? You can do gap analysis to see where the support is needed, and then plan with the government on how can the government close this gap. And then once you start developing the regulatory frameworks, it's a good practice to bring in international experience or international standards. But one thing that would be very, very helpful as well is that a series of discussions and close collaboration with the policymakers and the grid operators is very crucial at this stage, because you would like to make sure that what you are developing for them are fit very well in their context, and it also create the understanding for the government that you are working with on how to use the document and what the purpose of the document. And then the capacity building workshop by bringing in peers from neighboring countries. In our case, we invited speakers from Thai and Vietnamese utilities who are their neighbors and who are where the grid are connected to share the experience. That also helped to bring the confidence of the government official, and they can visualize better of how to implement the regulations that you are working with them. And then lastly, this is something I learned along the process, is that the perfect regulations actually do not exist, because once you think that your regulations are perfect, when you start implementing it, you will find that, okay, there's also gap here and some issues that you need to address here. And there's a trade-off between like trying to make it perfect, which will consume the time, and versus like in reality, the situation is already there. VREs keep coming up to the system. And so it's better to have even the imperfect regulation than not having anything at all. And you can keep revising the regulation along the way. And oops, what's wrong with that? Okay, so I would like to end my presentation with this, actually it's AI generated photo or graphic. And I think it represents our situation right now, that we have more VRE in the grid, and how are we going to live with it, because we cannot say no to this. It's coming, and how we can ensure that our community, our society live very well with the VRE penetration. Thank you for your kind attendance.
Yeah, Mighty One, thank you for that excellent presentation, and a clear indication that because we're going through a transition, many countries are going to need to look at their regulations. They're going to need to look at their grid codes. They're going to need to look at their laws and their policies to make sure that they're in line with what we're trying to do, and to create the enabling environment and the level playing field so that VRE can come in place in energy storage systems. Great presentation. Love the work that you're doing in this program, and I'm sure many countries will benefit from that experience. Next, I would like, and by the way, congratulations to the first three presenters, because you've been right on time. You're doing really well. So let's keep that going for the last three. So with that, I'd like to introduce Hazim Rosley, manager of the Carbon Trust, to present his paper on potential for on-site storage to drive investments in on-site renewables in the textiles and apparel sector.
Great, thank you so much, Matthew. Good morning, ladies and gentlemen. My name is Hazim Rosley, and I am from the Carbon Trust. So today I'll be presenting about an ongoing piece of work which looks at the potential for on-site energy storage to drive on-site renewables in the textiles and apparel sector. I'm from the Carbon Trust. We are a global sustainability and climate consultancy with the mission to accelerate the move to a decarbonized future. We work globally, and we have offices in Singapore, South Africa, UK, Mexico, and the Netherlands. Allow me to jump straight into the content. As Matthew has said, we have a strict time to keep to. So the Carbon Trust was commissioned by Apparel Impact Institute's Fashion Climate Fund to undertake a study that supports textiles and apparel manufacturing facilities, brands, and investors to assess whether on-site energy storage can support the business case for investing in on-site renewables. So it's a broad study covering a range of objectives that you see here. However, today I'll be presenting some initial outputs from the techno-economic assessment that we are currently undertaking. So a bit of an introduction. So we all know that global RE capacity has increased by over 200% from 2013 to 2022, and with almost 500 gigawatts in capacity added in 2023. This growth forecast is forecast to continue, and it is driven in particular by solar PVs. So clean distributed energy resources. So these are small scale behind the meter installations, which are situated near sites of electricity use, form part of this rapid RE expansion. So globally, approximately 80% of distributed solar PV installations are installed in the commercial and industrial sector. And this growth highlights the increasing attractiveness of distributed solar PV installations to this sector. We also see that there has been a growth in global energy storage capacity, and this is mainly driven by the expansion of grid-scale storage technologies. Behind the meter application only makes up a small portion, and it's only about 21% of annual added capacity. There are also very few case studies of behind the meter applications in the textiles and apparel sector, so it's quite new. However, we identified only one case study of where this has been deployed, and it is in Prokinol, where they have installed two 40-foot MTU battery containers with a combined storage capacity of 4.275 megawatts and 690 solar panels over a covered parking lot with a generation capacity of about 0.255 megawatt peak at its Costa Rican headquarters. So this allows the facility to save $41,000 every month by arbitraging the low tariffs at night and higher tariffs in the day. And it has also allowed the facility to avoid close to 300 tons of carbon dioxide equivalent in emissions annually. So essentially, what is the value of on-site energy storage, essentially? So on-site energy storage provide great opportunities to textile and apparel manufacturers. ESS can firm up RE generation by storing excess energy generated during periods of high RE generation and discharge energy during periods of high energy consumption or low RE generation. So its dual function as a load and generator asset allows it to be a source of uninterrupted power supply or backup power in the event of brownouts or blackouts. On-site ESS can also enable cost savings by reducing the costs associated with consuming electricity from the grid. So in regions where time of use tariffs are implemented, on-site ESS allow consumers to reduce their electricity bills by charging the battery during off-peak hours where tariffs are lower and discharging during peak hours where tariffs are higher. This is also known as load shifting. Co-locating storage and solar assets also provide the additional benefit of optimizing the size of the solar installation as it improves the investment efficiency of solar installations. So beyond providing site-specific benefits, on-site ESS can also provide value to the grid. And this includes the provision of ancillary services, such as your back start, your frequency regulation, your voltage control. ESS is a good source because it can inject electricity extremely fast and with higher accuracy than conventional generators to provide system reliability services. It can also reduce congestion in grids by storing electricity produced in times when the grid is too congested. So overall, we know that on-site ESS can support the overall decarbonization of the textile sector. However, we do realize that many of the revenue streams that we mentioned here may not be available in regions where textile manufacturing facilities are located. And this is what we explored in the techno-economic analysis. So we ran a techno-economic assessment to understand when storage might improve the business case for on-site solar. And to help with this assessment, we obtained the load profile for one tier 1 site and applied it to the cases of China, India, specifically the state of Maharashtra, and Bangladesh, with variations applied for variables such as time of use tariffs, CAPEX, and other country-specific factors. Here we ran a CAPEX investment model and ran several scenarios, a business as usual scenario, a scenario where the carbon price is $15 per ton of CO2, and another scenario where the carbon price is $25 per ton of CO2. So firstly, what we see is that batteries are useful when there is excess solar generated electricity than the demand from the site itself. So this excess electricity can then be stored and used another time when the tariff is higher or subsequently sold to the grid. The space and land availability is a key constraint. As we know, textiles manufacturing facilities are not normally very big and therefore don't have the space to install a lot of solar PV panels. So in this site that we looked at, the demand for electricity is often above the maximum solar capacity, as seen by how the blue lines on the graph are always higher and greater than the green lines. And so the high on-site manufacturing electricity demand on this location limits the need for electricity storage in sites with only space for rooftop-mounted solar. And therefore, the business case can only be strengthened if a site is sufficiently large or if a site enters into a private PPA to purchase zero-carbon electricity from an external supplier. So this therefore reduces the ability for the battery to provide capacity firming and optimizing values to the site. So the other thing that we can look at is also ancillary services. So in China, India, and Bangladesh, in these regions that we looked at, the lack of ancillary service markets limit the revenue streams that is accessible to storage and thereby reduces the value of storage too. Ancillary services tend to be provided by conventional thermal plants in these jurisdictions, but we know that ancillary services is also becoming increasingly important due to the higher penetrations of RE in the grid, and batteries can be a good source of ancillary services because of the almost instantaneous injection of power to the grid when needed. However, existing procurement mechanisms limit the ability of behind-the-meter storage applications from participating in ancillary service markets. Therefore, the revenue streams accessible to storage are limited in these regions and will remain limited until batteries can be remunerated for providing ancillary services. Now let's look at load shifting and uninterruptible power supply. So on-site solar and battery storage, from our analysis, is much more viable in India, in the state of Maharashtra and China as compared to Bangladesh. So we see that the business case is strongest in India, where the carbon price is at $25 per ton of CO2. The IRR is also pretty strong at 11%. It is also similarly viable in China in the same scenario, but however, this takes a longer time to pay back the investment, 12.5 years compared to the 9 years in the same scenario in India. And then this difference is largely driven by the design of the time of use tariffs in the state of Maharashtra. In the state of Maharashtra, the peak rates are charged over a longer duration, and the times where the peak tariffs are charged are more consistent with the times where the site consumes higher loads, and this is in the morning. And as you see on the graph as well, the viability of solar plus storage in Bangladesh is not as good, is quite poor actually, and this is driven by the higher capex of solar and battery into Bangladesh. So we also want to discuss China, and here we want to discuss China because although India has the strongest business case, adding storage does not actually improve the viability of investing in on-site solar. On-site solar is by itself viable in India. In China, however, storage improves the viability of investing in on-site solar. As we see here, solar and battery offer quicker paybacks than on-site solar only. However, the payback is realized only after 13 years, which is pretty long. Payback for on-site solar and battery will be below 10 years, only when the carbon price is at least $65 per ton of CO2, and that's about 5 times larger than the existing carbon price that China has right now. The internal rate of returns across all scenarios in China are decent at 7 to 8%, reflecting that on-site energy storage, on-site solar and battery is a pretty viable investment for textile facilities in China. Nonetheless, as mentioned before, we need additional revenue streams and opening up the ancillary service markets for participation by behind-the-meter applications is really useful and will be a key source of revenue for these sites. So a few key takeaways. So firstly, most textile manufacturing facilities do not have sufficient available area to install solar panels that sufficiently meet their site's demand. This means that the electricity generated from solar will mostly be consumed rather than stored in the battery and redeployed at a different time or exported to the grid. And this therefore limits the revenue generation potential from batteries. Large sites are better off and will be better able to capture the full value of having on-site batteries. Secondly, more revenue streams need to be enabled to enable site owners to realize the full value of battery storage. So this applies not just to textile sectors, but to all behind-the-meter applications as we start to look at industrial decarbonization. Policy is needed to allow for participation of batteries in ancillary service markets and for them to be remunerated sufficiently for providing such services. Lastly, if load shifting is the only revenue source for on-site battery applications, it will only be viable in jurisdictions where there is low solar and battery capex and where time-of-use tariffs are well designed. Carbon pricing will help. We'd also suggest revisiting import tax and excise duties linked to solar PV and battery imports, and where possible to explore subsidies to promote deployment in the short term so that there will be an increased deployment of behind-the-meter battery applications. So as I mentioned, this is just initial results from our work. We cover a lot more areas than what I've had the time to share today. Please feel free to get in touch if you have any questions. Thank you very much.
Thank you, Hazim. That was a very rich presentation, a lot of information, and a couple of quick takeaways. I love the message that you make that ancillary services and revenue for batteries are important. And I think in a distributed generation system where we are moving towards everybody being able to participate, providing that kind of revenue to whether it's commercial customers is going to be essential to get the kind of storage in a grid system that we have. The standard utility today of just wanting to sell electricity and not have everyone else participate in the market has got to change. The technology is giving us the opportunity to do that. I can tell you several examples where I've seen battery storage come in. One in particular I love in the US, school buses, which are only used during a short period in the morning and the afternoon, electric school buses are now becoming part of the utility battery storage system. The additional revenue that they get from the utility for being that battery storage backup allows the school buses to be actually a cheaper alternative to fossil fuel school buses today. And so we're going to see this revolution is coming, whether the utilities are ready for it or not. And I love the presentations that you have had here. All right, next one. I'd like to now invite Alex Campbell. He's the Director of Policy and Partnership for Long Duration Energy Storage Council, and he's going to present Long Duration Energy Storage, Unlocking the Essential Component of the Energy Transition. Alex.
Thank you very much. Good morning. The revolution is coming indeed. So I will certainly be talking about what we think is a bit of a revolution. So I'll talk about the LDES, Long Duration Energy Storage Council, a bit about the global need for LDES, the technologies, and then of course the policy and regulatory reform that we think needs to happen. All this information is available on our website, or if you want to come and get me afterwards if I go through it too quickly, please do. So who is the LDES Council? We're an industry association formed in 2021 at COP26, really with a mixture of companies who are all dedicated to the role of LDES in accelerating the energy transition. As you can hopefully see on the left, we've got the technology providers, but then we've also got the investors, the operators, and the end users, including some of the biggest companies in the world by market value, as you can hopefully see there. Just briefly on definitions. So we define LDES as the ability to discharge energy continuously for 8 hours or more. And that can go across days, weeks, can even be stored seasonally. Different organizations have slightly different definitions. US DOE says 10 hours, British government says 6 hours, but it's that kind of ballpark. And then last but not least, just a bit about our partnerships. So we're a founder member of the Global Renewables Alliance alongside wind, solar, green hydrogen, geothermal, and International Hydropower Association. You may have seen the XXX, tripling renewables by 2030, doubling energy efficiency. That was the GRA alongside multinational partners really pushing for that at the last COP. So I'm not going to linger on this one. Why do we need LDES? Hopefully you all know the energy system is changing. You know we need to decarbonize power. You know we need more electricity to electrify all sorts of other sectors. You know the sun doesn't shine all the time. You know the wind doesn't blow all the time. If you don't know that, you're probably in the wrong conference, or maybe it's good that you're here because you're learning some important things. So that shift is, of course, a difficult technical challenge to handle. I'm not going to linger on it. Again, happy to speak more afterwards if anyone wants to learn more. Why does LDES come in? So that previous slide suggests the need for flexibility. So this is a chart from a US agency. Lots of organizations have done the same sort of thing. The crucial point is, as you get more and more wind and solar, more of your electricity coming from wind and solar, so the x-axis at the bottom, the need for the length of the duration of the storage increases. That's when LDES comes in over and above the short duration lithium-ion batteries, which are fantastic and do an important role on grids today, but they're not suitable for 10, 12, 24-hour durations. And that's really when LDES comes in. What does that need add up to? So we did some work with McKinsey a couple of years ago. In a nutshell, to get to net zero, we found the potential lowest cost pathway would involve 8 terawatts of LDES technology. So that's about 5 of thermal, which I'll talk a bit more about in a moment, and 3 of power. And those are huge numbers if you're not aware of that, absolutely huge numbers. But the benefits are huge as well. System savings of up to $540 billion US per year to the global energy system if we get this right. And of course, massive carbon savings and so on. So huge potential prize from implementing these technologies to help manage the energy transition. So what are the technologies? Well, we group them into 4 families. That's mechanical, which includes things like pumped storage hydropower, which has been around for over a century, huge deployment globally, other well-established technologies like compressed air. Then thermal technology, so these take electricity, hopefully renewably generated electricity, store it in the form of heat, and it can be in really basic materials like sand, like bricks, molten salts, and then discharge that heat on demand. Could be turned back into electricity or used for heat applications. Chemical forms of storage, green hydrogen most obviously, and then electrochemical, so that the batteries. So as well as lithium ion, there's a range of other novel battery types, which all have slightly different use cases, longer durations, can be used in different contexts. So wide range of technologies out there, all falling within the LDES family. Just want to briefly touch on thermal storage because it sometimes gets overlooked. Hopefully you'll have been in some of the other sessions over the course of the conference talking about the need for industrial decarbonisation and the role of heat. I mean, I'll just pick the second bullet there. About 50% of all heat produced is used for industrial processes, leading to about 20% of global carbon emissions. We need to decarbonise heat, industrial heat. The good news is we have thermal energy storage technologies available today to serve a lot of those medium temperature needs. They're being deployed in Europe, in Australia, and in the States, around the world, really. They are there, they can be used, need some regulatory reform to get there, but I'll come to that in a moment. So just a really important point to note. Thermal energy storage paired with renewable energy means we can industrialize in a low carbon way. So that's kind of the good news. It's all fantastic. These technologies are amazing. They can help us decarbonize. They can support wind and solar and so on. Why aren't they being built at the scale that we think is needed? So, you know, there's a range of challenges, including with the first of a kind technology, investors not really understanding them, all these sorts of things. Probably the single key takeaway from me would be electricity markets aren't typically set up to incentivize the deployment of these technologies. So you think about offshore wind or nuclear or even transmission infrastructure, a lot of upfront cost, relatively low operational costs. Investors need to have their revenue visibility. They need to know how they're going to get paid back over how many years. We heard on the previous presentation, you know, payback periods of 10 plus years. It's the same for LDES technologies, but that kind of visibility, how that revenue, the certainty that the investors need just isn't there in so many electricity markets, which also feeds across onto the thermal side of things because of the link to things like grid tariffs. So lots of work needs to be done on the policy side of things. We have 3 set buckets, as we call them, of policy options, which can be used in different ways. On the right-hand side, it's kind of direct technology support, so that might include things like grants and incentives. On the left-hand side, so these are the key long-term market signals that policymakers can give. Carbon pricing, it can be phasing out the crazy fossil fuel subsidies we have around the world, setting targets for both renewables but also storage. That can really help to send some confidence to the supply chain. And then in the middle, those revenue mechanisms. And you know, there's lots of different types. In the UK at the moment, there's a consultation on something called a cap and floor, also used for interconnectors. There's variations on 24/7 clean PPAs, so the business sector can drive deployment, and then a wide range of other policy options out there as well. And just to finish up, I just want to give a quick overview of some of the things that are happening around the world. So in the EU, the new electricity market design is going to require EU member states to undertake a flexibility assessment. We think once that process is concluded, they'll see the need for LDES technologies. Already some EU states are working hard on this. So Italy is procuring LDES right now. Ireland has finished a consultation last year looking at options. Outside of the EU, the UK has just consulted on a quite innovative mechanism. And then in the States, you know, there's lots of support coming through the Inflation Reduction Act. India and China, you know, China's got fantastically ambitious targets on pumped storage hydropower, for example. So lots going on around the world. And just to kind of finish up on that point, there's money going in from national governments, which is great for both the short duration but longer duration storage as well. But importantly, the multilateral organizations are really starting to get their heads around this. So the International Energy Agency, its February 24 ministerial outcome document, talked about the need to set targets on storage. And the G7 in their energy communique from last month talked about setting a 1.5 terawatt power storage target for 2030, including short duration as well as long duration, but really important. So we are working with partners and stakeholders to hopefully at COP get a commitment to long duration energy storage and shorter duration energy storage targets into some of the outcome texts. So it really is a massively growing area, really exciting time to be involved, and we need those policy unlocks though. So yeah, there's my details. Please do get in touch, come to me afterwards or drop me an email, LinkedIn or whatever, and plenty of reports on our website. But thank you very much for your time and attention.
Thanks for that, Alex. And I think a vision into the future of where we need to go once we're going to net zero and total RE. And great to also see that many of the options aren't critical mineral requirements. And so something that we need to think about as we're looking at it. I've always said that the last link in the chain is storage in being able to go all renewable. And clearly long duration storage is one of them. All right, a final presentation before we open it up to the rest of the panel to answer questions. Sorry, is coming from Mr. Herbert Lubis, Director at PT Partogi Energy, to present his paper on review of lithium extraction suitable for Indonesia's geothermal brine. Again, I want to keep you on time so that we can have time for questions.
Good morning, distinguished ladies and gentlemen. My name is Herbert Lubis. I'm a practitioner of renewable and clean energy. Previously working on Indonesia geothermal Sarula project, 330 megawatts, the largest single undertaking in the world. First of all, I would like to thank the organizer to invite me to share our paper in this prestigious ADB forum. Why lithium? Because lithium is the cornerstone of energy transition for two reasons. One is a key ingredient for energy, like energy storage. Secondly, for electric vehicle and energy storage, meaning that we want to expedite, to accelerate renewable energy triple by 2030. So we are in line with the ADB program today. I would like to send messages from two of my friends in US. The first one is Professor Donald Sadoway from MIT. So he mentioned two things. First of all, battery storage must be cheap. Raw material must be cheap and available in the local area. And it has to be made easy to manufacture the battery. Secondly, we have a very interesting company in Boston. Both are in Boston. This is Emily from Pure Lithium in Boston. So her message is to make the next generation of battery, a non-flammable battery. This is the key messages that I want to send to the audience here, the importance of energy storage in the energy transition program to achieve net zero emission, let's say for Indonesia 2060 or earlier. So basically, what is this lithium? Lithos, Greek stone, is a light reactive material. It is very good and for excellent metal for electrical and heat conductivity. if somebody asks me question, how does it look, the product? Basically, when we extract the lithium from the geothermal brine, it looks like a salt, really like, white powder, and, very easy to recognize. This is the chart in Indonesia. We have a conference in Bali in G20 meeting that this is what we have in Indonesia, how we get to, the use of electric, what do you call that, energy storage. If you see this one here, about 50% of the storage is used for e-mobility, like two-wheel cycles, and then automobile EV, and the rest is for utility scale. This is our current situation. The lithium is not yet in the radar. That's why it's still zero. This is the current producers in the world. Number one is Australia, Chile, and China. And number 5 is, Brazil. So if we can if we can produce 3,000 tons per year in the next future, then we will overtake Brazil as a number 5 lithium producer in the world. So basically, this is a very basic technical matters. How you extract the lithium from the source. You can take it like in Australia, spodumene from rocks. And the rest is from, evaporation like in Golden Triangle. In Chile, it's like a evaporation in the salt bed lake. But what we have in Indonesia later is called direct lithium extraction method from geothermal brine, which is also available here in the Philippines. So basically, if you want to manufacture your factory, make sure the material is available locally, cheap, and secondly, make the battery easy to manufacture from local available cheap resources. This is like in Chile, it's like a traditional, and you can see from the traditional and from, you have to evaporate the lithium from the, in the ground for maybe 6 months or so. But with direct lithium extraction, it's a matter of hours and, days. This is best practice in the world. You can, read my paper, and then if you have any question, let me ask me question if you want. And also, direct lithium extraction method is very too technical. And what we have to do locally or available commercially is called adsorption technology, mostly done by, company, water and wastewater treatment company. This is what they're doing, and then they just implement what they have experienced in the wastewater treatment into the lithium extraction method. This is basically the flow chart where you have the final product is called lithium carbonate. So that's why this absorption method is already available in the market for implementation. This is best practice in the world. Mostly they choose absorption technology to produce lithium. This is what happened. You extract the lithium from production well, and then go to the manufacturing. And before you inject the water to the ground, you take the mineral. This is technology already, implemented, but not yet successful in US. The same. And this is the economics. Basically, the largest producer in the world is Australia, extracted from rocks, not from geothermal brine or from salt bed, like one in Golden Triangle in Brazil, or Chile and China. This is basically, you can take a look, my paper, the capex, the indication of the capex to produce the lithium. And then this is problems right now is before you extract the lithium, we have a problem with another mineral, is called silica. So before we inject the water, because we are taking the lithium from unused resources where they dump the brine into the pond, and then we take the what do you call that, lithium, and then after we take the lithium, we re-inject the water to the ground. But basically, we have the problem. The issue is what do you call that, silica content. We want to make sure that when we inject the water, it is we will avoid. It's called silica, like congestion, or like silica scaling in the what do you call re-injection wells. So conclusion, first of all, lithium is the enabler of energy transition. Secondly, DLE, or direct lithium extraction, shorten the process of extraction, not months or years, maybe matter of days or hours. The third one is called DLE. The technique is available in the market right now. Is called absorption technology, which is available in the market. The third one, what do you call it? Maybe the fourth one, the project cost estimate. We can do calculation. I can explain if you want to. They have some parameters, the flow rate, concentration of ppm in the geothermal brine. 5, we are still doing research on silica and scaling issue. 6, I think this is the most important thing. Before you produce the lithium, you have to make sure that you simulate the real situation by using what do you call that, pilot. And the cost maybe 1/10 of 1/20 of the project cost. I think that is the end of my presentation. Again, I would like to thank you, the organizing committee, and looking forward to a productive discussion. Thank you.
Thank you, Herbert, for that. And nice to know that we might be able to get lithium from sources without damaging the environment further in the process, because you're getting it from a source like geothermal brine, where you're also generating electricity from the geothermal plants. All right, this time I'd like to call up all of the presenters to the table, and we're going to open up the floor to discussions. I think we've had a really healthy set of presentations, very interesting set of presentations. They're at the forefront of this revolution that we're going through of introducing VRE and energy storage and decarbonizing the whole power sector. And I'm sure a lot of you in the audience have questions. So I see lots of hands coming up. The first one over here. Do we have a mic for the? And I also know the coordinators might have gotten some questions online, if you can let me have those.
Good morning, Amir Barghouth from Thematic International. Thank you for the great presentations. I'm curious if any of the panelists would share their thoughts on the relationship between the EV battery supply chain and the BESS supply chain. Do you see them as primarily competing for the same set of resources, material, financial, and human? Or do you see them as synergistic, reinforcing each other, achieving economies of scale, and helping advance the industry? Or maybe a bit of both? Thank you.
Thanks for the question. So a very quick answer from me would be, I think you said it, a bit of both, really. I mean, one thing I would say from a kind of slightly broader storage perspective is that your question actually illustrates why it's so important to go for a diversity of storage technologies so that we're not locked into just one technology type, which does have a huge demand from a completely different sector. But the feedback that I've certainly received from some of our members is there is a definite synergy between the two, but also a bit of competition.
So I would like to add, in the future, the hope is that actually transport batteries will be part of the solution. And so clearly we recognize that they need high density batteries for transport. So obviously minerals that will provide that opportunity should probably will have a higher value for transport. And then we saw some of the long duration energy storage systems for utilities. So my sense is the market, if you allow the market to play it out, it will allocate those resources in the best and most efficient way possible. at the most cost-effective ways. That would be my answer to that question. Question in the back.
Hello, thank you. So my question is for you, Alex.
Yourself.
Oh, Ruba Amarin from KPMG. So Alex, you mentioned policy reforms are needed to unlock LDES. But I would like to understand more. Is it more the market design mechanisms or the compensation mechanisms, or is it just a general lack of policy making? Thank you.
Kind of all of the above. It depends on the market. I mean, markets need to value the services provided by storage assets, and it's a bit easier for shorter duration technologies. They tend to have maybe smaller, relatively speaking, upfront costs, for example. But if you're providing an asset which might only be used once a week, for example, your revenue visibility becomes so important, because there's just a risk that you're not getting that income. So it's a long-winded answer to your question, but a bit of both. I think at the very top level, I would urge policymakers to assess their need as they deploy more and more renewables, so understand what their system flexibility needs are going to be, and then depending on the particular market that they have, introduce those revenue mechanisms or other market designs to unlock the investment, essentially.
Good morning, Roberto Martin from Green Heat Corporation. Commonly, the chemistry for ESS, BESS is lithium perophosphate, or like PO4. And after the life of this storage facility, is there a technology how we can dispose, or can we recycle this chemistry? Thank you very much.
It's a really important question, that how do we treat end of life of this technology? I think the solutions are there. We have, for example, where I'm from in Australia, we have a battery recycler who can fully recycle all those battery technologies back to raw materials that then get turned into production of new batteries. However, it's still a costly process. It's I guess roughly cost neutral in that manufacturing or recycling process, but in terms of the projects that I work on, getting the batteries back from remote locations or from the electric vehicle industry, from vehicles that have a crash that need to be then returned to this battery recycling facility, is an expensive part of the process, and there is a temptation, I guess, just to stockpile, which is problematic, particularly given the critical resources involved. So the solutions are there, but the supply chain and logistics, I think, needs work.
I think that's a very important question, and also comes back to, when we're helping countries develop their policies and regulations to adapt to VRE and battery energy storage, we need to make sure that they're putting in place strong policies to encourage or require recycling of batteries. Because when you start thinking in terms of where we're headed, and the numbers of batteries and the volumes that we're going to be talking about, you have to start thinking now about what you're going to do at end of life and recycling it. And clearly, some of these things should be recycled because they are critical metals. They're going to be valuable. And also, you don't want them necessarily in the environment for all sorts of reasons. And the worst thing we want to have happen is the VRE revolution end up having environmental problems like our fossil-aged, has resulted in this. I think it's incumbent on all of us to be thinking about this problem and to be ensuring that when we're working with governments and creating the enabling environment for VRE, that we are also including in there this issue. Thank you. Question? Yeah, please, I'm sorry about it. Take that. If you have a question, line up behind the next one so that at least I know, and I'm not missing you.
Thank you. My name is Bagus from Kasra, Asia, working from the UK Mentari. So thank you very much for the presenter, because one thing that I learned is about the ancillary service. So from the Mongolia, from Laos, and also from the textile industries. So do you have a kind of the suggestion how to enabling factors to create ancillary factors from David as well? So because it depends on the market structure of the electricity industries. So is there any kind of the recommendation or suggestion to how to create and calculate the ancillary service, particularly having a potential of the battery and of the capacity of the battery energy storage? Thank you.
Thank you for your question. So for capacity enhancement, of course, there's financial issue. And how to say, market structure for battery. So for our case, we are working on ancillary service rule, which promotes market structure. And if there is available financing, we can promote renewable energy with the best. This is my answer.
Concerning the policy or solution for short term, for instance, I asked yesterday the panel here, when you open the factory, solar panel in our country has a limited regulation like local content. So the company must open factory in the country. Secondly, how do you open the factory? You have to have a complementary to open a factory of PV panel plus the storage battery. You have to complement each other to arrive at, like base load 24/7, and then obey the local content, open a factory in the country, both the variable renewable energy, including wind, and the storage system. The question is, where do you get the raw material from? As I mentioned today, where the material, like in the Philippines, you have geothermal here. Take the lithium from the geothermal brine, unused resources, waste. It's just like a scavenger. I'm like a scavenger, like crab, living in the bottom of the ocean, collecting unused material, then I eat. That's what the essence of this battery factory, including long duration energy storage. Long duration energy storage material like embry from Boston, it is from calcium and antimony. It is available everywhere. This is the byproduct from gold mine, and then dump it as a tailings, and you take it for free and make the battery from cheap material, make it easy to manufacture the battery, and from lithium, as I mentioned this morning, make the battery anti-flammable. Pure lithium, you don't need additional nickel or cobalt, which is very, very difficult to find. Make pure lithium anti-inflammable and anti-explosive. That is what the future of the battery energy storage system. Thank you.
Yeah, thank you so much for the question earlier. I think in terms of recommendations for allowing remuneration from ancillary services, I think it's quite hard to say that there is one approach that works better than others. It depends on how the electricity structure, the electricity market is structured in the country. So in liberalized markets, you may have ancillary service markets where various bidders can participate in the market, provide bids, and that could be an option for, there'll be an easier option, I would say, for behind-the-meter applications to provide ancillary services. In a country like Indonesia, where I think you're based because you're delivering the Mentari program, it's a single buyer PLN control system. So I think it's a bit tougher, to be honest. I think it's more of then how one option would be to perhaps have policies that enable the export of solar generated electricity with the participation in ancillary service markets paired together, perhaps. That could be one idea that I think of. But I think there are various options, and it depends on the procurement routes. And I will say there is no single silver bullet to boost provision of ancillary services. Thanks.
Thanks. Next question, please, and thanks for being so patient.
Yep. Hi, Evan Woolard from DNV and our solar business in Singapore. I really appreciate the kind of diverse experience on this panel, and I think with respect to my question, what I'm kind of coming at in the solar business through so many years in Asia, I think there's a wide variety of EPC contractors with various capabilities able to design, build, and construct projects of a kind of relatively large size. I'd be curious to the panelists' thoughts around, by extension, solar and storage projects, particularly on the medium and large scale, how you see the capabilities and maybe quantity of qualified contractors in the region able to undertake such projects. So yeah, thank you very much.
Yeah, it doesn't directly relate to my presentation if we're talking about the medium and large scale, but my experience in the Australian market and the construction companies that we're working with there and the companies that are delivering projects that are typically like battery and solar integrated projects between sort of 700 megawatts into the gigawatt range, is that there are quite a number of very experienced now companies doing that sort of work, and they're global companies. They have equal representatives in the Philippines, for example. A number of these companies operate throughout Southeast Asia. I'm pretty confident that there are good capabilities and good experience now in delivering these projects at that sort of scale. So it's fine.
Yeah, I mean, I would just add that, clearly that's a capacity that needs to be built, but knowing Asia and how it reacts in markets, I have no doubt that if the demand is there, the capacity will come. Look around, look at what China's been able to do in such a short period of time. As a continent, I find this continent very resilient, very innovative, and yes, it's an issue. Trained labor is important. But I think we need to have the demand, and I really think we need the policies and regulations to open the market up to allow this to happen more clearly. Yeah.
If I could just quickly add one more point on that. So with the newer long duration energy storage technologies, very commonly they've got off-the-shelf components. We're not talking about a fundamental change in the skills needed. It's not like nuclear fusion or something like that. It's pretty straightforward. Yes, people need to be trained and skilled, but it's not a huge paradigm shift. It's more a kind of minor adjustment.
Next question, please. We've got 5 more minutes for questions.
Hi, I'm Madura Watanabe from USAID SPP. My question is for Hazim, but for the other panelists as well to address. With textile manufacturers, but also other manufacturers that you've been working with, what is the motivation for their deployment of on-site solar BESS or other VRE? Is it cost savings, or is it to meet their kind of corporate decarbonization goals? And have you mostly worked with the big manufacturers? And can you talk about, like, what about the medium, small and medium kind of links in the supply chain? Any challenges in deploying these technologies for them? Thank you.
Great, thank you so much for that. I think there are various motivating factors that move manufacturing facilities in the textile sector. I think first and foremost is if the market mechanisms that are implemented in the country enables them to actually generate cost savings, then it's clear. That's the key driver that helps them to move. The second is textile manufacturing facilities usually supply finished products to global brands such as your H&M, your Nikes, your whatever brands. So those global brands, those corporates, most of them have set net zero targets. And their net zero targets include a reduction in their Scope 3 emissions. So these brand Scope 3 emissions are essentially the emissions from the textile manufacturing facilities. So there is also the push from brands on manufacturing facilities to decarbonize. And while this is not prevalent, there are some brands that are helping textile manufacturing facilities to decarbonize. And that is also another push to get them to implement on-site solar. And the other thing is, manufacturing facilities are also realizing that given that brands are moving in that direction, the way for them to continue to secure contracts to supply goods to brands is for them to decarbonize. And this is because brands are facing regulatory pressures, and they're also facing pressures from the consumer who want more sustainable products. In terms of challenges, they are plentiful, I think. From what I showed earlier, I think even though there is pressure from brands, the business case may not always support the implementation of on-site solar. So as we saw earlier in Bangladesh, the financials make it very challenging. And that's why it's been hard to move in Bangladesh, for example. But that's where sometimes the direct involvement of the brand can actually help the textile manufacturing facility to move. So we've seen, I can't remember the exact brand company right now, but what we've seen is that there is a global brand that has helped to actually fund and develop a wind project in Bangladesh that supplies directly to a textile manufacturing facility. And this direct involvement and support from the brand has actually helped to decarbonize the operations from the textile manufacturing facility. So that's just one example, and it's very heavy-handed involvement. It's good to see that, but I think it's something that we don't expect to see it more, I would say. So ultimately, the key challenge is really the business case, and the policy environment in countries need to be amended to really support increased investments in on-site solar and also on-site batteries.
All right, we're 2 minutes away from ending, and I'm going to take the prerogative of asking the last question for a flash answer, all right, going across the panel. So asking the panel, as we look forward into the future, what do you see as the biggest challenge going forward to open this market up to wide-scale VRE and energy storage systems in as short as you can? Going down the panel, all right?
Also supply chain.
I would say regulations.
I probably would say I don't know. I suspect it'll be a challenge that we're not yet sure of.
Lack of targets from national governments.
Yeah, for our country, regulation plus financing.
Open a factory, open your battery factory locally, complement with the VRE energy. Thank you.
So thank you. What I found interesting, nobody said financing. Oh, you did? Did I miss that? All right, financing. Absolutely. I mean, all of these are important. And, because we're buying a whole power plant up front that can store energy, it's very capital intensive. And one of the things in the next session I'm going to be participating in is to help the bank think about what it takes to finance the transition. And the transition is going to be capital intensive. And we need to find better ways to bring long-term, low-cost capital to the markets, or this is not going to happen very well. So anyway, with that point, I want to thank the audience for your patience in listening. I want to thank this fabulous panel for all the work they did to prepare their presentations and to come here to Manila to present it. I found the session to be very stimulating in terms of thoughts and challenges and ideas that we have to face. And so a round of applause for them, please.